So thank you very much, Hugo. It was a really great introduction, and I have nothing to add, only that today I'm going to present. Can you see the pointer? Yes. Okay, great. So what I'm presenting today is a joint work with Thomas Ducatz. Thomas is a professor at Sorbonne Paris Nord. He's been one of my PhD advisors, and he also invited me to Paris a couple of months ago. I gratefully acknowledge this. And okay, so let's start with the talk. So as Hugo said, I am interested in harmonic analysis and dispersive PDEs. Lately, I've been working more on harmonic analysis, and this is my opportunity to do something with nonlinear partial differential equations. And I'm going to use methods which are really not very much harmonic analytic. It's more, will be a talk in PDEs. So the first slide, this is perhaps the most important of them all. Here I want to present the PDE that I'm going to talk about and the associated problem. I'm going to present the phenomena I want to study. This is what asymptotic behavior means. And most importantly, I will try to spell out all this PDE jargon. You see, this is full of blow-up, scattering, stable, and all of this. I'm going to try and explain. So let's spend a few minutes here. Okay, so the cubic wave equation is this PDE that you can see here. It's a bit difficult. It's dissociative to look at two things at the same time. Anyway, this is called the cubic wave equation. This is a semi-linear wave equation, which means you have a linear part that is the wave, the ordinary wave equation, with a semi-linear perturbation. So I put here a semi-linear. That means that it does not depend on derivatives. This is semi-linear. Okay. The space variable will always live in a tree. The time variable will live in an interval. I stands for interval. Okay, so I'm going to say something about the interval in a few seconds. The problem I study is the initial value problem, which means that I give you a pair of arbitrary inputs, arbitrary initial data. These two are two functions. I write them in bold notation. This bold notation is going to be used the talk, is common in this subject. And I prescribe that the function u, the solution to our PDE, and its time derivative equal at initial time, at time 0, the given initial data. Okay, this is the Cauchy initial value problem, the simplest initial value problem. But this is going to be important. Okay, this is then a piece of notation. I'm going to speak about this functional space in a moment. This is going to be the space in which we will do everything. But first, let me spell out this I. I is the time of existence. So this PDE, this is called the focusing equation. I'm going to explain this in a moment. But its most important feature, and this is why I put this in the first bullet point, is that it supports blow-up solutions. Blow-up means that the maximal time of existence. So the solution, we're talking about functions of two variables. One is time and the other is space. In time, there is no guarantee that your solution exists forever. And indeed, it does not. When it does not, which means that the interval I is properly contained in R, we say that blow-up occurs. Okay, blow-up is one of those meta words that doesn't have a very precise meaning. Here, I'm just saying blow-up means a finite time of existence. Okay, it can be blow-up in the future, it could be blow-up in the past. And this is a very important example here. So this is a solution to that PDE. And you can do the computation even in your mind. If you differentiate this function, this is a function of t only. So here there is no Laplacian. It's a very easy computation, but it's going to be really important. So if you drop this Laplacian, this becomes an ODE, and that function there solves it, because if you differentiate it twice, the exponent becomes a -3, right? So it's very simple, but it's very fundamental. And so this, imagine if you put a minus sign here, when little t equals big T, this blows to infinity. And this is what we say. So the ceases to exist. Okay. This is the main example of blow up, which is supported by this PV. Okay. Now, this answer immediately answers the question: are there blow up solutions? Yes, here's an example. But now it's a very good time to introduce this quantity here, which will also give me the opportunity to do a bit of gymnastics with this bold notation. So this quantity, let me write it down explicitly on the blackboard. And people at home probably don't see the blackboard, but it's not a big problem. This is just, I just want to spell out the notation. So what is this here? I take this a calligraphic H1 norm of a bold. So the bold means that I have here two functions, u and the derivative of u. Okay. Calligraphic H1, so Sobolev norm of order 1. I need to put one derivative here, and I take the L2 norm. This is an integral on R3. And 0 derivatives on the time derivative. Okay, because this is how the wave equation works. Okay, you always need one less spatial derivative on this function. Okay, so this is what's written there, and this is this integral, and then there is an L4 norm, which is, notice that the L4 norm has no bolts, so it's just the function u to the fourth. Okay, so this is, and there is a minus here, very important. Okay, so this is just to practice with the notation, but this is an important quantity because it's conserved. So a priori, you see, it depends on t, but this is just a number. It's a finite number. And this, if you stare at this long enough, you realize that this is the reason why this equation has blow-up solutions. Because you see here, you have a conserved quantity that is the difference of two positive quantities. So it is possible that the energy is conserved because there are two positive quantities that both diverge. Okay. If I had put a minus sign here, this would have been a plus, and that would have been a completely different behavior. Okay. So this is why I wanted to introduce the energy, also because it's going to play a role in what follows. So now let's go to local well-posedness. This is another typical keyword. What does this mean? So I keep talking about solutions, but a priori nobody tells me that there are solutions for all initial data. Well, this that I'm pointing now is a theorem that tells me if my initial data have at least 1/2 derivative in Sobolev sense, then there is a solution. Maybe it exists for a very tiny time, but it is there. And also, local well-posedness means several things. It's continuous in the topology of the Sobolev space, and it's unique. Most importantly, we're talking about something that has a meaning. And here I have the opportunity to introduce this exponent, which is going to be extremely important in the form. 1/2. So 1/2, you see, is the endpoint for local well-posedness. And the reason for this is the scaling invariance. So I haven't written it in here, but you will have no problem in doing this mental exercise. If you rescale all variables, t, x, and u, appropriately, you can produce new solutions for all. So if you have a solution, you rescale it, and you get a new solutions. The L1, the S equals 1/2 norm, the Sobolev norm order 1/2, is precisely the one that is invariant under the scaling. Okay, and this is because this is the reason why it's important. But the manifestation of this, the first manifestation of this, is that Your problem is local well posed in this space and in higher regularity spaces. Now, these two bullet points served a double purpose. First, I want to convince you that H1 is really the space in which we should work. And second, I want to introduce another asymptotic behavior. So by the way, I didn't say it in the beginning. When I say asymptotic, of course, it's asymptotic in time. So I want to take a solution, let time go as far as I can, or in the future or in the past, and see what kind of behavior I find in the limit. This is the problem I'm studying. We have seen blow up. Blow up is one possible behavior. And now let me introduce another behavior, scattering. Scattering means asymptotically linear. So if you take a solution that in the long run, in an appropriate topology, converges to a linear solution, so a solution without the cubic term, that's a scattering solution. So in particular, the scattering solution is global. Okay, scattering solution exists for all times, and in the limit, it's linear. Intuitively, a scattering solution is small, because if you have, here you have a cube, right? So it's basic intuition. If you have a small number and you cube it, it becomes even smaller. So if you have a solution that at some point is small, you can imagine that the evolution will make the nonlinear term even smaller. And so asymptotically, you don't see the nonlinearity. This is the idea, but this is not obvious. And indeed, the right spacing, because I said small, but what does small mean? The right space in which to measure such a smallness is this critical Sobolev space. Okay. Yes, exactly. Yes. Okay, so this is, moreover, you have scattering is stable, yet another PDE keyword, which means that solutions form an open set. So if you perturb a scattering solution, you still have scattering. All in H1 half. And so far, this is all textbook material. This last bullet point is non-trivial. This is a theorem, Dodson and Lowry. I am lying a little bit here. This only holds for radial functions, but they have lots of partial progress in the non-radial case. I don't know where they are. It's very likely that this theorem is true, even though it's proven, strictly speaking, this is only radial. But my solution is going to be radial anyway. So, yes, if you are radial at initial time, you're radial forever. And radial means spherically symmetric, by the way. So this theorem reads: bounded implies scattering. This is not trivial. This is not true for other PDEs. For example, if you put a 5 here, this is false. This is rather a subcritical thing, but let's not add more keywords. Okay, so bounded implies scattering. So let's leave this slide. This was a kind of a crash course in the cubic wave equation. What are we studying? Asymptotic behavior. Which kind of asymptotic behaviors did we see? Two kinds, blow up and scattering. And what is the intuition? Scattering is small, blow up is large. This is the intuition. Okay, so now let's go to the result. So I'm going to present examples. So I'm going to build a family of solutions and then tell you what happens in the far future and in the far past. So let me start with the future. Okay, so here I am only this picture describes the asymptotic behavior in the future. So this plus means that t is bigger than 0, it goes to plus infinity. Okay. This PDE is time reversible, so you really need to go forward in time, backwards in time. Okay, and this is the result. So we are able to solve the PDE with this extremely concrete initial data here. I am just hiding here two irrelevant constants. The initial data is this. It's parameterized, as you see, by two numbers, a point in R2. And depending on the location of this point in R2, you see one of three behaviors. Close to the origin, so if this point is small, you have a scattering solution. Scattering was asymptotically linear. Away, so if you are big in the sense that you are away from this threshold, by the way, I call this function a threshold function, beta, it's an explicit function. And so away from this threshold, you have blow up infinite time, same thing here. And what happens exactly on the threshold? So of course, it's the most interesting question. You see a behavior that is neither blow up nor scattering. Because these solutions taken with the initial data on this line and this line are global, so they exist global in the future, plus global means global in the future. So they exist for all future times, but they are not scattering. So they are not asymptotic to a linear solution. So this is a third behavior, which was not included in the general slide, the first slide, the textbook slide. Say. Right. So this is only the future, and now this is the complete picture. Here I have future and past. I don't know if, I hope you can read. So what's written here? This is a scattering, plus and minus means scattering in both time directions. And then I have blow up plus and minus, same here, and here. And here I have a mix of blow up and scattering. Okay, great. So, so this is the result. This picture is the result, basically. Because I said examples, and this picture is, so what I like about this is that admittedly it's a bit messy. It's blow up scattering is hard to remember without a picture. So here's a picture. Why do I think this picture is the right one? First of all, remark one, the topology that you see in this plane, so the distance from the origin, x and y. So x is the abscissa and y is the what's the name for that? The y-axis. I forgot. And coordinate is the coordinate. This is the same as in Italian and Portuguese. Thank you very much. So the distance from the origin here is exactly the norm in the critical space. So what is this picture? The way I like to think about it is the following. So we understood that the right space for initial data is the scaling critical subgroup space, H1/2, Hilbert space. That's a huge space. We would like to know, given a point in this space, or given a pair of initial data, what is the asymptotic behavior? This is the question, the big question. Give a criterion that allows to, we don't know how to answer, but here we take a slice of it. So this is a plane in H1/2 because the topology is exactly the right one. And on this cross section of the space of initial data, we can say exactly what's going on. Okay, so here we see an illustration of the general principles of the first slide. You see, for example, we said the scattering, small data scatters. Indeed, you see here open set, this eye-shaped region is open, in which you see scattering in both time directions. There is this intuitive idea that big solutions should blow up. This is very hard to make precise. And indeed, this is the point of all of this. But at least we see here, if we are sufficiently away from the origin, we will blow up either in two directions or just in one direction of time. And then perhaps the most interesting thing, we have these threshold solutions. These are global non-scattering in the future. These are global non-scattering in the past. And we have these four spatial solutions, which are global and non-scattering, both in the future and in the past. Okay, so we have, in our result, we characterize all three behaviors, so scattering, blow up, and threshold. But when you give a talk, you have to make choices. So let me focus only on the threshold behavior, which is, in my opinion, the most interesting, which we observe. So how does a threshold functional solution look like? The answer is in this diagram here. So this is a representation of space-time. Here you have time, and here you have the radial coordinate, x. This is the so-called light cone, which is when t equals x. This is very important in the wave equation. So roughly speaking, and for t that goes to plus infinity, so for big T in the future, these threshold solutions look like this old friend of us inside the light cone. And a linear solution, I mean, this is a bit misleading because this happens also for big time. Okay, so this should be here, but there's no space. But so here we don't really know what's going on. But for big T, we see that solution inside the light cone and the linear solution outside the light cone. So so first of all, what is this? Remember we had this square root of 2 over t plus t. This is a ODE solution. Okay, so this is a solution to the cubic wave equation without the Laplace. Okay, but it's so this would blow up at the origin, but we are very far away from the origin. So this is not a blow up solution. It's a kind of blow up. It's a kind of ODE decrease. Okay, this is the simplest ODE solution. So you expect that this should play a role, indeed. And outside you have a scattering. So the convergence to ODE is both pointwise. So what does this mean? Fix a point x and let t go to infinity. Eventually you see square root of 2 over t with the remainder of t minus 3. Remember, these solutions are classical, okay? So they are smooth, finite energy, and so you can do pointwise estimates. Makes sense. We also do a LP estimate. This is inside the light cone. You see this goes to 0, provided P is sufficiently big. Outside the light cone, we see scattering. So what is scattering? Actually, scattering, we have a scattering in this H1 sense, which is the energy space of the wave equation, but still. Okay, so this is related to Ugo's question. So what does scattering mean? That when t goes to infinity, outside the light cone, this norm goes to 0. It's H1, it's not H1 half. It's also because H1 half, it's non-local. So how do you localize H1 half? Because you have a fractional Laplacian, you see. So whereas this is that. So this you can look at. This is just the integral on. Yeah, it's a technical thing. But up from this, we see scattering in this H1 sense. Okay. And then this final example. So this is a first feature of this result, which I like. So there is, we call Dodson and Lowry. Dodson and Lowry proved that bounded implies scattering. This is not scattering. So it must not be bounded either. And indeed, it blows up like a log. And this is yet another, this is grow up, because you don't because you don't really want to say blow up, because you see, it's how somebody came up with this great idea of grow up.
Boundedness implies scattering in H1 half, right, for the whole space.
Yes. Right? Yes. Yes. H1 half.
Yeah, but the original result of the Dodson and Lowry is also scattering in H1 half, but not in H1 half.
This is A1 half.
Yeah, in the first slide, boundedness.
Oh, boundedness in H1 half.
Scattering in H1 half.
Ah, yeah. Yes, absolutely.
Scattering outside the cone in H1, the other one is scattering in H1 half.
You are right, but that's true. You are right. But anyway, I am sure this is not scattering in H1 half.
Sure.
Maybe I should say so. Yes, you are. Yeah. Okay. So this is not a scattering solution. Definitely
Yeah,
not.
of course, yeah. The other result is getting.
Yes, you are. You are right. Yes, that's absolute. Scatter. Yeah. Yes. Yes. So this is a different notion of scattering. Yes. This is. It's an interesting point to think about. But anyway, so this is the grow up. We believe that this should be equal. Anyway, we're still. So we believe that this is really a log, not bigger than a log. Okay, so this is how the threshold solutions look like. And now let me compare these solutions with what is known in the literature. So, or otherwise said, why do I think this is interesting? So, of course, this is one of the oldest models that has been studied since forever. Maybe even Einstein studied this. But it is relatively recent that people have been asking about this threshold. This is this keyword threshold here, which is so threshold means it's this intuition I said. Small is scattering, whatever that means. Big is blow up, whatever that means. What's in the middle? So the first paper I have. So here again, I'm not trying to be exhaustive in the bibliography, but the main conjecture on this, and the first, is this paper of Piotr Bisoni. I actually asked my Polish friend how to pronounce it. But I have no Turkish friends to ask. So I would just say Zenginoglu, hopefully. They conjecture that so here this is a literally almost a cut and paste from the paper. So you see that the conjecture is not a precise conjecture, it's more of a numerical observation. But still, they say that this threshold between, because this is what they observe numerically, this threshold between scattering and blow up should be given by a codimension 1 manifold of global solutions. They don't say what this means, but I mean, it's because they don't say in which topology, codimension 1, but say. So a codimension 1 is like a barrier you cross of global solution, which look like this. And this formula here, we saw it. This is exactly what our functions, our solutions look like. We have something to say on this -4, but this is a minor technical thing. This is the profile, point-wise. And actually, they kept studying this problem because they have there is this paper with Roland Donninger and Daniel Zenginoglu. They do find such a codimension, a manifold of threshold solutions. They find it. But it's codimension 4, not codimension 1. And the convergence to this object here is a bit different. So it's L4 on a region that you see it's close. It's inside the light cone. There must be a bit of air or space between this QT and the light cone. And also the rate of convergence, I mean, let me go back to the previous slide. The rate of convergence, if you do P equals 4, that's exactly -1/2 that you find here. Okay, so that's it. That's really similar, you see. And also this is also, so these two, I wrote these two equations. We have several estimates, but I chose these two because they are exactly the ones that appear in the literature. Okay. And however, so this almost solves this problem, but not really, because these are not solutions to the Cauchy initial value problems. They change the problem. They take a problem which is called the Goursat problem. So they put initial data on a light cone, and they use a different notion of energy. So these solutions are not bona fide solutions to the Cauchy initial value problem in the critical Sobolev space. Okay, so this hints that that should be right, but not in the framework which I introduced in the first slide, which is and this is the reason why I spent so much time on that. That's really the framework we would like to understand. On the other hand, the solutions I showed you are solution to the Cauchy initial value problem, finite energy, and also in the critical Sobolev space. Okay, so this is why I believe they are interesting. Okay, so now let's go and build these solutions. So yes, so I didn't say why I like the cubic wave equation. It's a fundamental. There are several reasons why it's, in my opinion, a very good model for nonlinear blow-up, for wave blow-up. But it also has a bigger property. Usually people call it the conformal wave equation. And the reason this is in this slide, because if you take conformal map, so conformal map, there are two things in this slide which I am hiding under the rug. The first is this. What does Lorentzian mean? So the conformal map is angle preserving, but not in the Riemannian sense. I'm not going to explain what this means. What does this mean? But intuitively, it's an angle preserving map. And if I use this to do a coordinate change, so I pass from my coordinates tx to tilde, or tilde t, tilde x. So this omega, what is omega? Remember, we said a conformal map preserves angles, right? So this means that angles are preserved, but distances can be scaled locally. The Jacobian determinant measures how volumes are scaled locally, and you take the fourth power. 4 is 3 plus 1, so the dimension of the space in which we are. So this is a measure of how you are scaling distances at each point. This is a function that measures how your map scales distances at each point. So maybe I should. This is a function of t and x, or t tilde and x tilde. Okay, so this is a really a function. And what is the fundamental property of conformal maps for PDEs? It is this one. Maybe you have seen this. If you're familiar with elliptic PDEs, you've seen the Kelvin transform, stuff like that. That's exactly the same. Right? So, but there you have the Laplacian. Here you have the D'Alembert. But the algebra is the same. So if you change variables conformally, you have a very nice formula for the D'Alembert. And what is really important here is the numerology that appears. So you have here a 1 and here a 3, which means that when you go to the cubic wave equation, you modify this term with the conformal change. So you get the omega cube. And then you modify this term by simply defining a new variable u tilde, and it's a cube. These two simplify. Okay, so this is a very simple algebra, but this is really the reason why the cubic wave equation is the only semilinear wave equation that enjoys conformal invariance. And now I'm going to do this with another conformal map that is not valued in R1 plus 3, is manifold valued. You can do this the same. There is only a caveat. When you put a manifold here and not the flat space, this Laplacian needs to be changed. And this is something I'm not going to explain, because I should start mumbling about scalar curvature and stuff like that, and I don't want to do this. But let me just say an important thing. If this manifold is the sphere, then this new Laplacian must be changed to a Laplacian plus 1. So the new D'Alembert, the D'Alembertian on the sphere is this. Okay, so this is the D'Alembertian plus 1. This plus 1 is going to be important. Okay, so let's do this in pictures. This is the picture of the map I'm going to use. Maybe I used this in another talk already, so I'm shamelessly recycling this one, but not the next one. So I definitely use this for other talks. I don't know if this in this setting or not. Anyway, so this is the map I want to use. Okay, so remember we have our space with variables. I introduce a radial variable r. The time variable is always the same. I introduce a new space with tilde variable, tilde t, tilde r. What is tilde r? Is the radial coordinate on the sphere. So the distance from a pole, say the North Pole, you fix it once and for all. And once you have this, you can use this map, which is based on a composition of arctangents. This map is conformal. So we can apply the theory that we saw in the previous page. What is the geometry of this map? Well, you can say it takes the space-time and it squishes it into this triangle-shaped region. Okay, so this red line is so horizontal lines get mapped to these horizontal lines. Most importantly, what I want to highlight is that the initial value, so when you do the initial value problem, you post your initial data here. And this line, this is t equals 0. If you do t equals 0 here, you get tilde t equals 0. And if you can do the computation, great. Otherwise, just imagine this. Imagine this graphically here. So this is adapted to the Cauchy initial value problem. Okay, so this is important because that's what we want to study, and that's what is the relevant difficulty here. Okay, and so now it's called because no, it's called Penrose because Penrose introduced it for the first time. So is it related to the tilings? I don't think so.
No. It's related to this. Okay.
The tilings are related to this?
No.
Ah. Yes, here we have. Just is much more expert than I am on these things. So it's hard to lecture. So this is why I'm a bit shaky. Okay, so I hope I'm not saying anything too terrible. But anyway, so now I can finally tell you how we construct these solutions. So what are we trying to do? We're trying to construct solutions to the cubic nonlinear wave equation, which is this. We have at our disposal all this conformal theory, which tells us that we should define a new function in this way. This omega is an explicit function, which I didn't write here because it's not really relevant. And now this is the idea, which is extremely simple. And it's indeed, every time you construct explicit solutions, in the end, you always reduce to an ODE. The idea is to reduce to an ODE with the Penrose map. So we ansatz that after doing this change of variable, our U tilde is a function of time only. And if we do so, we have an ODE now, because remember, we had a D'Alembertian plus 1. The Laplacian is not there anymore because we dumped it. We do the ansatz to eliminate it. And now we get an ODE, which is very similar to the one we studied in the very first slide when we dropped this, but there is a plus 1. And this makes a world of difference. So we see a much richer dynamics now. This is called the Duffing ODE, by the way, if you really want to give names to things. Now, this is an ODE. So by standard theory, so it's an ODE posed on this line, say, you can forget about this triangle for almost. You pose initial data here, and you have a solution to the ODE which exists in an interval. This ODE is also supports blow-up solutions. So it might be that the ODE blows up. However, this is the last and fundamental thing I want to say. If you blow up after P here, then you are scattering in the original space. Okay, so this is, I hope this geometry is clear. So this line here corresponds to this hyperboloid in the physical space. If you let the line go past pi, the hyperboloid disappears. So you exist for all times. And so I'm talking about this case here. If this t plus is strictly bigger than pi, you exist for all times, and you're also bounded, because you are essentially a ODE that exists for all times, so it has a maximum and a minimum. You can prove this directly, but remember Dodson and Lowry. If you are bounded, you scatter. And indeed, that's what happened. If you explode, blow up past pi, when you pull back on physical space, you scatter. If, on the other hand, you blow up before pi, when you pull back to physical space, you blow up. You blow up on that hyperboloid here. This is the blow up region. And so in particular, this is the origin is where you first see a blow up. And if you blow up in Fenrose space exactly on pi, then you see the threshold solution. Okay, so this is the construction. And that's it. I'm done. Thank you.